Hello, my name is Thomas Nyman. I work in Ericsson Product Security. It's my pleasure today to present this joint work with my colleague Merve Gulmes from Ericsson Research and Hosham Elateli and Professor Ashokan from the University of Waterloo in Canada. This is, so that doesn't work, but this works. So this is sort of like a research concept we have been looking at, and the motivation for this is this sort of like looking beyond memory safety. So we are also interested in looking at sort of building side channel protections on top of CHERI. And this is sort of like both memory safety and side channel leakage are challenges that are particularly relevant for cryptographic code and security critical software. So this is the kind of things that if you are building, secure enclaves on top of application class processors that will run software crypto, this should be sort of relevant for you. So the conventional way you would protect this cryptographic code is by programming it in a way that is constant time. So this prevents side channels, but it's extremely difficult to implement constant time code correctly, right? So a particular challenge today is that with heavily optimizing compilers, the compiler itself might be working against you when you try to ensure that your actual implementation is constant time. And CHERI hardware naturally, of course, addresses the memory safety hardening challenge, but it doesn't defend against side channel attacks. And a difference between sort of this side channel leakage is with memory safety, you are often made aware of memory safety problems by software crashing or misbehaving. But side channel leakage happens silently. So you don't really know whether your software leaks unless you actually try and mount a side channel attack against this. So the concept which we call BLACKOUT extends CHERI with something called blinded capabilities and hardware enforced stain tracking. And together, these provide a way to mark secret data in registers and the memory subsystem and propagate this sort of like information about what is secret throughout arithmetic and logic operations. And that allows the BLACKOUT processor to actually enforce that code that is supposed to be constant time operates in this so-called data-oblivious manner. And that means that it can actually detect when this code will leak a secret and fault. So it makes side channel leakage visible to the programmer in a way that's conventionally not possible. And we have an implementation of BLACKOUT on the CHERI-enabled Toooba core, and I'll talk a little bit about our evaluation towards the end of the talk. So really briefly about sort of side channel leakage. So you can look at side channels as unintended outputs of a system where there is some timing dependence on a secret piece of data, right? And there are many root causes for this, both the logical and functional properties of processors, as well as how arithmetic circuitry is implemented. So the link here is to one of my currently favorite blogs. So this is Ken Scherf blogs, who basically looks at old classical hardware through like a very large microscope and kind of reverse engineers this. So if you look at, for instance, how arithmetic circuitry in like old Pentiums are implemented, these are extremely complex and have different paths for different types of value, which introduce this kind of like timing difference. And then something that's a very sort of hot topic in the security conferences is like this speculative execution attacks, right? So this is another type of root cause that can cause this side channel leakage. Here's kind of like a very simplified examples of how this happens. So if you have a code, and this is sort of roughly how you would do like a substitution box lookup in like an AES implementation. You have like a piece of secret data that gets used as an index, and in most cases the compiler will actually derive like a pointer or capability out of this. So now you have a secret value that's effectively being used as an address, and this will have an impact on the microarchitecture level on the caches. So if you have this kind of code, an attacker who can somehow observe these effects on the cache can effectively try and use this cache behavior to probe for which cache line is being used and learn something out of this secret value through that, right? And in most cases, this is sort of not that straightforward. You have to sort of repeat these kind of experiments over time. But in practice, this is sort of like a practical way to break cryptography, especially on devices to which the attacker has physical access. So potential mitigations for this on a microarchitectural level would be to isolate or partitions these microarchitectural resources. But this generally has like an impact on all software running on the device. And so if you work extensively with C++, there is like this design principle in C++ that's called zero cost abstractions. And that means that generally they'd want to have designs where if you're not using a feature, you don't pay a performance cost. So only software that uses a particular feature should have a cost. And this is one of sort of the things that is sort of inspired us in this Blackout work. So we are so in Blackout we are building on this patterns of building software in a constant time manner, and specifically we sort of provide this property of data-obliviousness. So these programs where the execution path and memory access patterns are independent of the input data. And this is in practice achieved by writing the software in such a way that there is the behavior of the software will not use secrets in decisions when doing branches or when addressing memory, as in the example we saw earlier. Excuse me. But one of the challenges in actually devising data-oblivious programs is that even if the program is data-oblivious on a source code level, optimizing compilers can actually introduce side channels into the generated assembly even from a data-oblivious program. And to sort of address this, there is a kind of a previous work in academia that provide these data-oblivious instruction set architectures that are designed to enforce this data independent behavior on specific pieces of code. And this is generally enabled through hardware taint tracking, very similar to what we use in Blackout. Sort of two notable pieces of prior work here is the oblivious instruction set architecture, or OISA, and blinded memory architecture, or BLIME. But generally, when these architectures need to track where the secret information is propagated in memory, they use memory tagging. And memory tagging is very difficult to scale, right? So if you need to track multiple different strands of data, this cost of memory tagging becomes very high. So we had the idea that how about we build a data-oblivious instruction set architecture on top of CHERI, and instead of memory tagging, we use CHERI capabilities to track this tainted data in memory. And on a higher level, our goal is to provide a unified, efficient hardware-software solution for memory safety and side channel protection building on top of CHERI. But I think this is sort of, one of these takeaways of this talk, I hope, is that even if you're not interested in sort of side channels per se, I think they are definitely these kind of benefits of looking at CHERI as a foundation of building this kind of overall solutions that go beyond memory safety, right? And I think this is like a challenge in the broader industry, right? When we see these hardware features that are very much discrete and are addressing single attack vectors. And I think we most need more of this kind of work that is actually looking at multiple threat vectors simultaneously when designing hardware features. So in our adversary model, we are sort of building on the the same model as in CHERI, but we are looking at then mitigating side channel attacks that are mitigatable data-oblivious code. We exclude some of these trans-execution attacks that are actually able to influence data accesses from another security context, such as meltdown, and we also exclude transit capability forgery, but there is prior work in this space to actually mitigate these for CHERI as well. So in Blackout, we have this notion of blindedness that is used to taint the raster files and the information that's being transferred between rasters by arithmetic operations and others. And loads and stores from blinded rasters must occur through these new blinded capabilities. And blinded capabilities architecturally are ensured to have exclusive access to their area of memory, which we call blinded memory. And we have extended the compiler and software stack to provide some sort of software level invariance to support that. But the key takeaway here is that blinded capabilities now turn silent side channel leakage into something that can be explicitly reported as an error to the programmer. So on the hardware level, what the hardware actually enforces is that for this blinded information that has been obtained through blinded capabilities, it will not allow this information to be used for control flow decisions or as address operands in loads and stores. And the only instruction set level changes we have introduced to CHERI is a new permission bit to track blinded capabilities. And then we have some special handling for when you actually need to spill blinded rasters into memory that's been added to the capability store and capability load instructions. So I think I will skip this over this in the interest of time. So here's some evaluation numbers. So we evaluated this blackout design on the CHERI-Toooba on the VCU118, and because the main hardware changes are really just introducing this blindedness bits into the raster file. This actually has very low area overhead. There's a little bit more of a like moderate power overhead at 5%. And then we have performed performance evaluations on CheriBSD. And note here that what Blackout provides is like a way of enforcing that code that's supposed to be data oblivious, in fact is so. We are using these benchmark suits from prior work, in particular OISHA. And using this benchmark, we measured a 1.5% overhead as a geometric mean. There is some outliers there which we able to identify to, I think, mostly sort of specific sort of artifacts in like the software support. And then remember that we want to have this sort of notion of a zero cost abstraction. So we don't want this to add an overhead for software that doesn't use blinded capabilities. And this we evaluate using the Cormat benchmarks. And in this, we have a negligible performance overhead. All right, that's my time. So I will So for more details on the security evaluation, I'll refer you to the paper. But as a summary, Blackout combines CHERI memory safety with this side channel confidentiality through blinded capabilities. If you have questions, me and Merve are here all day, so please come up and talk to us. And there is the conference paper. So this is our work published at ACM-CCS earlier. Last time I checked, the proceedings are not yet available online, but we have a preprint available at this URL for more technical details. Thank you very much.